Hello, guys. All right. So, good afternoon. We're almost at the end of this semester. So today we will finish chapter 6, which is the last major chapter for this class. And Tuesday next week, we will do a practice session for chapter 6. Thursday next week, 29th, we will do the last chapter, chapter 7, okay, which is pretty short. Then the last class of the semester is April 4th. Okay, so we will do the final review before the final exam. Okay. Today, finish chapter 6, okay, section 6.7, small sample test for difference between. All right, and we also do similar things for confidence interval. We have large sample test, confidence interval for difference between two means and a small sample. Same thing from here, chapter 6. Okay. So when the sample size is small, we know already we use students' t distribution, the t value. Okay. For t value, we have degree of freedom and also the half alpha. Okay, half z. Then there's actual requirement. Both population needs to be normal. Okay, follow a normal distribution. Then we can use students t distribution. Okay. So here is the setup. Okay. So x1, x2, xn, and y1, y2, yn are small samples from normal population. Again, this is condition. Mean value, mu x, mu y, standard deviation, sigma x and sigma y. Okay, and also these two samples need to be independent to each other. Okay, the general condition is sigma x and sigma y are not to be equal. Okay, so not known to be equal. Okay, so if they are equal, we have a different set of equation. Okay, but the general case is these two values are not equal. Then this is the setup for the test. Okay, so depending on how H0 is set it up, okay, so mu x minus mu y less than or equal to, larger than or equal to delta 0. Okay, then we calculate V. V is the degree of freedom for t value. Okay, so which is a function of sample standard deviation x and y, sample size and x and y. Okay, so we calculate degree of freedom V and down to the nearest integer. Okay, so we have done similar things before. Okay, then we calculate the t value based on this. This is sample mean for x and y. Okay, delta 0 is whatever delta 0 we want to check. Normally it is 0. Okay, then this is the sample standard deviation x, y, and sample size x1. Okay, so we calculate the t value, and then based on the degree of freedom, we get the t value. Okay. From there, we calculate the p value, p score, okay, which is again based on how h1 is set up. Okay, so it's the same setup as other situation. Okay, so when h1 is mu x minus mu y larger than delta 0, then p value will be to the right of 0. Less than to the left, not equal, two tails added together. Okay, so same thing as before. The only difference is the equation here. Okay. All right, let's work on this example number 8 together. Okay, again, from here, can we conclude that we know this is a chapter 6 question, hypothesis test, and whatever after conclude will be H1. Okay, so we mentioned this many times, will be H1. Okay, so good website design can make web navigation easier. One paper present a comparison of items recognition between two designs. Okay, so that's compare two designs. Then a sample of 10 users. Okay, so from there we know this is a small sample. Okay. So use conventional web design, average 32.3. Okay, so keywords average, we know this is about mean value. Okay. And then standard deviation, okay, 8.56. Another sample, 10 user, small sample, with a new structured web design, have another average and another standard deviation. Okay, so clearly this is about hypothesis test for difference between two means, and the sample size is small. Okay, so this is question from section 6.7. Okay, so we know use the equation we just discussed. Okay. Remaining will be, first of all, we write down the parameters needed, which is given. Okay. And set up the null hypothesis and alternative hypothesis. Okay. So the alternative hypothesis, the mean number of items identified is greater than with the new structure design. Okay, which is mu y minus mu x larger than 0. Okay, equal to mu y larger than mu x. Okay, so this is H1. Then H0 will be the opposite of H1, mu y minus mu x less than or equal to 0. And then we plug in the number into this equation. First of all, the degree of freedom equation, okay, is a function of xx, sx, xy, nx, and y. Okay, and then we plug in to calculate the t value. Okay, to save us time, degree of freedom is around 17. Okay, and the t value based on the equation, it is 2.82. 2.82. And then we found out the p-value. Okay. So the p-value is depending on how h1 is asked. Okay. So h1 here is mu y minus mu x larger than 0. Okay. For larger than 0, that's the first case here. The p-value is the area to the right of z. To the right of z. Okay. So the t-score is 2.82. 2.82 is here. Okay. For students, t-distribution, it doesn't give us exactly p-value, but it gives us a range. Okay, so 2.82 is corresponding to, is between 2.567 and 2.898. Okay, for 2.567, it is corresponding to 1%. For 2.898, corresponding to 0.5%. So we know the p-value is between 0.005 and 0.001. Okay, so p-value less than 0.01, less than alpha. Okay, so alpha didn't tell us. We use 5%. Okay, so the conclusion is we reject H0 and we conclude H1 is true. Okay, so H1 is true. Okay, and you can copy the whole sentence after the keywords conclude, because that is H1. That is how we set up. Okay. So yes, we can conclude that the mean number of items identified is greater with the new structure design. As you can see, all these different situations, the procedure is the same, just different set of equation. And next class, when we discuss the practice questions, I will show you two sheets which I write down all the equations side by side together. Okay, so you can quickly pick which equation to use depending on the question. Okay. So the about question assume the two variants are not equal, so unequal variance. Okay. In a special situation, when the two variants are equal, okay, both of this is under difference for small sample for difference between two means. Okay. But this is a special situation when the variants are equal. Let me see, this is less common. Okay. Still require normal distribution, still require independent to each other. Okay. But if they are equal, then a new set of equation. Okay. So new equation is here. SP is a special number for sample variance, okay, which is the function of nx, ny, sx, and sy. Okay, so use this equation to calculate the so-called SP, and you can plug SP into the equation for students' t-score. Okay, so different equation, same t-score. Okay. For the degree of freedom, okay, Okay, here is the equation I missed here. Let me write down. Because for t-score, we need degree of freedom v. For this case, the v will be nx plus ny minus 2. Okay, so you can use this information to look at table 8.3. To find out the p-value is the same, exactly the same, depending on how each one is set up. Larger than to the right of t, less than to the left, not equal sum of two tails, exactly the same. Then let's practice this example number 9. Can we conclude that this will be H1? Okay. Then let's read. So we have two methods has been developed to determine equal content of steel. Okay. In a sample of 5 replicant, 5 small sample of the first method, X. Okay, on certain type of steel, average measurement, so that is mean value. Okay. The standard deviation of this. Another 7 sample for the second method, another mean and another standard deviation. Okay, so this is the hypothesis test for small sample for the difference between two means. Okay. Here, the sentence assume that it is known that the population variance are nearly equal. Okay, so this sentence tells us we should use the equation here, assuming equal variance, not this equation for unequal variance. Okay. And x 5 and y sx sy. Okay. So H1 tells us there's a difference in the mean measurements. So that's a difference. So H1 will be mu x minus mu y not equal to 0. Okay, so that's a difference. Okay. So H0 will be the opposite, mu x minus mu y equal to 0. Okay, and then we calculate SP. Okay, so SP based on this equation, function of nx and y and ss sy. So calculate SP, it turned out to be this much. Okay. And then the t value is on this equation. Okay, so the sample mean for x is 3.16. Here. Okay. Sample mean for y is 3.24. Delta 0 is here 0 because this is delta 0. Okay. Not equal. Then SP is what we just calculated. Okay. 0.0457. And x and y. Okay, so we calculate t value is minus 2.990. Okay, and the degree of freedom nx plus ny minus 2. Okay, so that's 5 plus 7 minus 2. That's 10. Okay, so based on this information, we look at table 8.3. And it turned out because H1 is set up as not equal. Okay, so when it is not equal, we need to add it 2 tails, the sum of areas in the 2 tails. So that's the third situation. Okay, so because the t-value is minus 2.99. Okay, so the 2 tail will be minus on the left of minus 2.99 and on the right of 2.99. Okay, so it turned out that value is between 0.05 and 0.01. Okay, but because this is 2 tails added together, the p-value will be between 2 times 0.005 and 2 times 0.01. Okay, so that is 0.01 and 0.02. Okay, so 0.02 is still less than alpha, assuming to be 5% if alpha is not told in the question. So still we can reject H0 and conclude H1 is true. Okay, so we can conclude, you can just copy here. We can conclude that there's difference in the mean measurement between the two methods. Or H1 is true. Okay. If there's no questions, let's continue for section 6.8, which is for pair data. Okay. We also did that for pair data for confidence interval. Okay. So that's the last situation for hypothesis test. Okay. So for pair data, we can, for each item, we can measure 2 things. Okay, so basically, for example, the example of we trying to compare the new tire and old tire and run like cars, okay, for 1,000 miles or 10,000 miles, and we compare the wear for the new tire and old tire. So for each car we have like a new tire, the other one is new materials, the other one is old materials. Okay, so this is an example of pair data. Okay, so for pair data, we have x1, y1. Okay, so x1, y1 is in a single sample. Okay, so then the difference, so d1 is the difference between x1 and y1. Okay, so d1 and dn are sampled from a normal population. Okay, so this is a condition has to be following a normal population with a mean value of mu d. Okay, the mean value of the difference between x and y. Okay, so depending on how H0 is set up, again, the equality line always go to H0. So that's another rule. Calculate the t-score. Okay. So t-score, this is sample mean for the difference. Okay. So this is the mu0, which we want to check. SD is the sample standard deviation of the difference, and is the sample size. Okay. Then calculate the p value. Same thing as always, depending on h1, larger than mu0 to the right of z, less than to the left, not equal, two tails added together. When the sample size is large, okay, so which is, of course, means larger than 30, then the requirement for D to be normally distributed is no longer needed. Okay, because when sample size is large, it doesn't require to be normally distributed. But when the sample size is small, it needs to be normal. Okay, so this is the similar situation as before. Okay. Then, if the sample size is large, we no longer need to calculate the t-score, the t-value. So we calculate the t-value instead. Okay. So for pair data, depending on the sample size, large sample, we use z value and no longer required to be normally distributed. For small sample, we use t value and it is required to be normally distributed. Okay. So this is example. Okay. So when a table is given, we know this is for pair data. Okay. So this is about muscle reflex when stimulated through the electric impulses either to motor points or to nerves. Okay. Article report study in which both methods apply to upper arm regions of each of several subjects. So the total number of subjects is 7. So that's small sample. Okay. So small sample, we use t value. The latency time was measured for each subject. Result shows here. Okay. So we have 2 either through nerves or through motor points. Okay. For nerves, that's the value. For motor points, that's the second row. A difference between these two is, 59 minus 56. So that's the difference. Okay. 57 minus 52 is 5. Okay. So can we conclude that this will be H1? So let's assume for nerve is X, for motor point is Y, the difference is here. Okay. And from there, we can easily calculate the mean value for the difference, which is all the difference added together divided by 7, sample size 7. Okay. Okay. And standard deviation of the difference, okay, can also calculate it, just the square of all the difference added together, like 3 square plus 5 square plus 2 square plus 6 square plus 3 square. Okay. So minus 7 times the mean value square divided by n minus 1, 7 minus 1. Okay. So then the standard deviation is 1.60. Okay. Because the sample size is small, we use students' t distribution. But first, we need to set up H0 and H1. Okay. So H1 there is difference between nerve and motor point. So when there's a difference, means mu x minus mu y will not equal to 0. Okay. So h0 will be the opposite, mu x minus mu y equal to 0. Okay. The degree of freedom is n minus 1 is 6. Okay, so degree of freedom will be n minus 1 for students' t distribution. Okay. Because the sample is only 7 less than 30, we calculate the t value based on the equation. Delta 0 is 0. Okay. Average of the difference is 4.286. Okay. 1.6. And it's 7. Okay. So the t value 7.08. Okay. So turned out from the table 8.3, p-value is less than 0.0105. Okay. So which is less than alpha of 5%. So we can conclude H1 is true, which means there's a difference between these two measurements. Okay. All right, so far we have discussed all the situations to do hypothesis test. Okay. The way to set up H1 and H0 is almost the same, always the same. Okay, so H1 is whatever after can we conclude that? Okay, so that will be H1. Okay, H0 will be the opposite of H1. Another rule is the equality line always go to H0. Okay, and then depending on how the question is asking, we have 7 or 8 different set of equation or more than that. Sometimes the variance is equal or not. Okay, so we just select the right set of equation. Then we calculate the p-value. Okay, the p-value is depending on how H1 is asked. Okay, so rather than to the left, less than to the right, not equal, the two tails added together. Okay, and then we compare p-value with alpha. Normally alpha is 5%. Then we draw a conclusion if p-value is less than alpha. Okay, if it's less than alpha, then H1 is true. Okay. So that's the way we do hypothesis tests. Okay, so the last part, almost the last part for this chapter, we talked about power. Okay, so what is power, first of all? So at early part of this chapter, we know, right? So that's two type of error. That's two type of error. Okay. So type 1 error is when H1 is not rejected when it is actually false. Okay. And type 1 error is can be controlled by alpha. Okay. So the power of the test is defined as the probability of rejecting H0 when it is false. Okay, so which is equal to the opposite of type 2 error. Okay, so type 2 error is fail to reject H0 when it is false. Okay, so the power is the opposite of type 2 error. So that means the higher the power, the smaller the type 2 error. So that's good. That's good. For type 1 error, it's easy. Okay, so we can keep one error small by choosing the alpha. So alpha is the level of mistake we can make. Okay, so alpha normally is chosen as 5%. Okay, so type 1 error is less than alpha. Okay. For power, if power is large, okay, then that means type 2 error will be small. Okay, because power is the opposite of type 2 error. Okay. So then the probability of type 2 error is small, then the test is a useful one. That's good. The purpose of to calculate the power is to determine whether or not a hypothesis test is likely to reject H0 in the event that H0 is false. Okay, so basically the larger the power, okay, the better, okay, because the smaller the type 2 error. Okay. So in this section, you need to know what is power. Okay. So very simple. Power is the opposite of type 2 error. Okay. And what is type 2 error? So type 2 errors, as we discussed before, is the error we make when we fail to reject H0 when H0 is actually false. Okay. Here we just discuss how to calculate power. Calculate power. The calculation is not easy. Okay, I just show you the procedure to do that. Okay. Do not need to expect some calculation problem for your final exam about power. Okay. But anyway,
I'm sorry, did you say we can expect to or cannot?
You do not need to. So no need to practice the calculation for power. You need to know what is power at least. Okay. All right. But anyhow, I will discuss the procedure and give you an example. So calculate the power has two steps. Okay. The one is to calculate the rejected region. Okay. And then we calculate the probability that the test statistics, such as the mean value, fall within the rejected region if the alternative hypothesis is true. Okay, which means H1 is true. Okay. And that is the definition of power. Okay. If power is not large enough, we can increase the sample size to redo that. Here is an example to calculate the power. So find the power of 5% level tests. Okay. For the setup of H0 for mean less than 80, less or equal to 80, versus H1 for mean larger than 80. Okay. For the mean yield of new process under the alternative mu. Okay. So the alternative mu is needed, is necessary to calculate the power. Okay. But for hypothesis test, we do not have the alternative distribution. Okay. So assuming n 50 and sigma is 5. Okay. So the first step is to get the rejection region. Okay. So that part is easy. Rejection region. For the null hypothesis, so X will follow a normal distribution with a mean value of 80. and the variance of, okay, so 5 is the sigma, 50 is the sample size. Okay, so that is the null hypothesis. No distribution, sorry, no distribution. And under this no distribution with a mean value of 80, okay, and let's calculate the rejected region for 5% level. Okay, so when it is 5%, okay, and this is the rejection region. Okay. The z-score based on table 8.2 can be calculated as 1.645 to have a right-hand tail of 5%. Okay, and from there we can calculate the value of mean value. Okay, 80 plus the z-score 1.645 times sigma over square root of sample size. Okay, so that is 81.16. Okay, which is here 81.16. So the rejected region actually is what? It is if the mean value larger than or equal to x.16, 81.16, we will reject H0. Okay, so that is the rejected region. Then the next step is to find the power. Okay. To find the power, we need the alternative hypothesis. And we need the alternative distribution. Okay, so the alternative mu is 81. Okay, 81. So let's do the next step. Find the power. Okay, and the alternative distribution will be with a mean value, new mean value of 81. Okay. The variance will not change, same variance. Okay. So let's draw the null distribution and the alternative distribution together. Okay. For the null distribution, the mean value is 80. Okay. For the alternative distribution, the mean value is 81. Okay. And under alternative distribution, okay, the reject value will be 81.16. So larger than 81.16 will be rejected, as we discussed here. Okay, 81.16. So our goal is to calculate the probability for 81.16 under the alternative distribution. Okay, how to do that? Still, we calculate the z-score. For z-score for the value of 81.16, when the mean value is 81. Is 81. Okay. So the z-score is only 0.23. Okay. It turned out the probability, the areas is only 40.9%. Okay. So the power is not very high. Okay. So the power is probability that the test statistics fall within the rejected region if the alternative hypothesis is true. Okay. So the power is only 40%. Okay. So that's the power. Okay. Which is pretty small. All right. So anyway, this is the power, the introduction of power, and we have an example of how to calculate the power. Okay. So we need one new information, which is alternative mu, to be able to calculate the power. Okay. But of course, the focus for this chapter is the hypothesis test, okay, as we discussed in section 6.1 to section 6.7. All right. The last two sections for chapter 6 is pretty short. Okay. Section 6.14, as you can see, we skip some of the sections, okay, which is not very important. So right now we are at section 6.14, multiple tests. So sometimes it is necessary to perform many hypothesis tests. Okay, so if that is done, if more tests are performed, then the confidence that we can place in our result will decrease. Okay, so in other words, for example, remember for hypothesis test, if the p-value is calculated to be less than 5%, then we'll reject H0 and we conclude H1 is true. Okay. But if we perform more and more of these hypothesis tests, it is difficult to tell which rejected H0 are really false and which are a type 1 error. Okay, which means we reject a true H0. Okay, so when we perform more than one hypothesis test, we should make some modification. Okay, and how to make the modification is pretty simple. Okay, we call that Faraday method. Okay, so how to this method provides a way to adjust the p-value when we perform multiple hypothesis tests. Okay. So if the p-value remains small after the adjustment, okay, then the null hypothesis can still be rejected. Okay. The adjustment is very simple. Okay. The adjustment is simply multiply the p-value by how many tests we have performed. Okay. So for example, if we perform 4 tests, okay, then the p-value will times 4. And here give an example. So for different coating formulations are tested to see if they reduce the wear on cam gears to a value below 100 micrometer. Okay. So no hypothesis, mu larger than 100 micrometer, is tested for each formulation. Okay, we have 4 hypothesis tests for 4 different formulations, and they have 4 different p-value. Okay, so the smallest p-value is for formulation C, which has a p-value of 0.005. Okay. Okay. So we know formula C may be effective because the p-value is very small. Okay, but we also know the p-value of 0.005 is unreliable because we performed the for hypothesis test. Okay, so we need to do the Bufferini adjustment, okay, which is 4 times the we do for hypothesis test, so times the p-value of 0.005. So the p-value, the new p-value will be 0.02, still less than alpha of 5%. Okay, so we have strong evidence to conclude that formulation C is reactive, even though we performed the for hypothesis test. Okay. All right. The last section for chapter 6 is, to use simulation software to perform hypothesis test. Okay, so we can use simulation to test many different hypothesis tests. For example, difference between two population means depending on the sample size. So all different type of hypothesis tests, we can do that using simulation. Of course, we can also calculate the power. Okay, using simulation as well. Okay, and that's the end for chapter 6. Okay, so the last major chapter for this class. Okay, so what we did for chapter 6, so we learn how to draw conclusion from result of hypothesis test. First of all, how to set up H0 and H1, and how to draw conclusion based on different situations. So large sample test for population mean, okay, small sample test for population mean, okay, and test for population proportions, okay, and also for difference between two proportions, okay, and also test for difference between two means for both large sample and small sample, and also for special situations, for example, when the variance of two populations are same or not the same. Then lastly, we discuss hypothesis test for pair delta. Okay, and don't forget the definition of power. You do not need to understand how to do the calculation yourself, but and know what is power mean. Okay, so that's the end for chapter 6. Tuesday next week, we will do a practice session for chapter 6. Hopefully, we can finish that session using one class. And then Thursday next week, it is for chapter 7, which is the last chapter. Then we have one more class, which we will do a final review for the final exam. Okay, so that's it for today. Any questions or comments? All right, thank you guys. We're almost there. See you Tuesday. Oh, also I upload the homework for chapter 6, which will start right now. You have about 2 weeks to finish. Okay, thank you.